Hi everyone, super happy to be speaking here at Puget Sound. My name is Iswarya Murali. A little bit about myself. I'm a senior data and applied science soft. In today's presentation, I'm going to talk a little bit about my pet passion project, where I combine two things I love, data science and the musical Hamilton. Before I go into the talk itself, why am I doing this talk? By Hamilton, right? So I'm a huge fan of data journalism. I'm really passionate about data science and visualization, all those fun concepts accessible to people in a bite-sized, digestible form. So the power of telling a story using data is extremely underrated. And I find that if you sprinkle in a little bit of sugar with your medicine, so to speak, it makes that process a lot more exciting, and the prospect of bringing new people to data science a lot more enticing. So hopefully Hamilton fans will have a little bit of fun along the way. If you're not a fan, this inspires you to stick to the musical. So without further ado, let's get started. So about this agenda, so I have two different data science applications that I'm going to show, both of which make use of the same data set of Hamilton lyrics. The first is a network graph. I'm going to show how you can transform a flat CSV file and visualize it as a social network between the characters. And once we've constructed that graph, we can use graph theory concepts to identify and quantify importance of various characters within the musical. The second part is how to extract engrams from the song lyrics. And I've also used the engrams as my features to build a random lyric. All of my code is in R, and I will share it at the end of this presentation. So let's jump real quick into the social network. I am using iGraph library within R. Right. Before we move on, a quick refresher of graph theory concepts. So this is an image I picked from Wikipedia's page on network graphs based on editors' contribution to pages in different languages. So the circles are called vertices, or alternatively nodes, and these are the entities, in this example, they are the language themselves. So they are the entities between which you want to demonstrate a relation. And the lines connecting two circles or two vertices, they call an edge. And the thickness of that line, if you see, it's in some cases it's 10, some cases that line is of a much thicker width, and that is relative to the strength of relationship between those two entities. And it's usually defined through an incidence function or a weight function, which is basically a relationship between each pair of vertices that we're trying to plot over here. So in this scenario, the edge function could be a relative weight of the number of editors who contributed to both languages. So what we want to do for our example is to represent the characters of Hamilton in a graph similar to this, that we can visualize the relationship. So people who work in data science, this famous quote, 80% of a data science project is spent on cleaning the data, and 20% is spent on complaining about the need to clean data. So I can truly attest that the hardest part of any data science project is actually engineering and getting access to the data, and fortunately, that difficult bit of wrangling is already done. I have this nice clean CSV of Hamilton lyrics that someone has uploaded on Kaggle. So we can just simply download it and use it directly from that link. So the CSV has 3 dimensions, title, speaker, and lines. So let's take a moment to just explore this data set. So if I were to visualize this data set as a dynamic decomposition tree, I can see it's a sort of almost a hierarchy. So there's that title, so that's the name of the song. And for every song title, there's a speaker and the respective line of lyrics spoken or rapped by them. there's one record in the data set per song, per speaker, per lyric. That's how it works. And by the way, the visual that I'm showing here, it's pretty nifty. It's called a decomposition tree. I'm using Microsoft Power BI to visualize that. It's really helpful for root cause analysis and drilling deep into multiple dimensions. So once we know that this is the data set, so that's our original data set, and our desired output is a graph that looks something like this. But so what we need to do is convert that flat file into a graph. How can we do that? The first step is to transform that flat file data set into one that is more conducive for graphing. So in this scenario, what I'm creating is an n-by-n adjacency matrix, n being the number of characters, with a weight that is associated for each pair of characters. So on the columns and the rows, these are all the characters, and the numbers between each pair is the weight of the relationship between them. Now, this weight can be anything that you choose to decide. You know, it can be however you want to decide the entities or the relationship that you want to graph. In this scenario, I've chosen the number of songs that feature both, say, a speaker X and speaker Y, or my M and N, as my weight function. The assumption is that two characters appearing together in the same song have a strong relationship. So in this scenario, you can say Angelica and Hamilton have a relative weight of 10, which means that they appear in like 10 songs together. Hamilton and Burr, they appear in 42 songs together, so they obviously have a relationship. So once I do that, once I get this matrix, it's pretty easy. It's like 2 lines of code to convert that into an iGraph object. Just all you have to do is just like pass this adjacency matrix, and then you can just plot it with an R. So this part is the hard part, and once you get that, it's relatively easy to get that matrix. So, all right. So here's a result of me plotting the graph object from the adjacency matrix. We just converted that flat data set, that CSV that you saw, into a network plot. And it's not bad. You know, you can see all the characters here. You can see the lines connecting them. But I'm sure we can do better, because this graph, it's very basic. It doesn't provide a lot of context on that relative relationship. And that was the point of that weight function, right? So can we take it a step further? This is much better. So you can see the thick lines connecting certain pairs of characters that visually they indicate a stronger relation. And how did I do that? By specifying the thickness of the edge as a function of the weight instead of a static number. So the graph on the left, I've just given like edge weight equals 1. So you know that it's uniform across the graph. The second graph is a function of the weight. So visually, it just packs a punch, and it's a lot more intuitive too. So once we do that, the next example that I want to show is it's pretty cool library. It's called This Network, and the graphs in the previous example, they were static, they're just pictures. But this one, click on this. This is a dynamic graph. So it allows you to drag and move things around, enlarge parts of the graph to just double click into certain relations. Very nifty library. It's called This Network in R. So now that we built a graph, and visualize that, we can do a lot more with the construct of representing data. And a big advantage of building network graphs is so that we can apply graph theory concepts. In particular, we can use centrality to identify which vertices, which nodes are the most important. And important can mean different things depending on the context and the problem at hand. It can be in relation to the type of flow or transfer of communication across a network, or a measure of cohesiveness of the network itself. In the simplest terms, it's just how significant is an entity relative to all other nodes around them. And what this means is that there are many different definitions of reality. And just like with a numeric distribution of data, where you might average or median or mode or standard deviation, depending on the context or the problem you're trying to quantify. You might want to choose a different kind of centrality depending on the context itself. And because there's a lot of centralities, I'm going to focus on just 3 for the Hamilton graph and see if we can extract those. The first and simplest is a degree centrality. By the way, as I'm talking through these centrality measures as a fun guessing exercise, you might want to just consider or put in the chat and Q&A box which characters you think might have the highest and lowest degree centrality. But what degree centrality is, it's simply the number of edges connected to the vertex. You would simply count the number of links, number of lines that connect to a particular vertex, and each vertex would have a different degree centrality. There's also a concept of in degree, meaning how many nodes link to a particular vertex, and an out degree, meaning how many outgoing links does the node have. But our graph doesn't have any direction, so it's undirected, so which means out degree are the same. Hopefully you had an opportunity to think about the degree centrality with respect to this graph. And the answer is no surprise. So Hamilton and Bird, the 2 major characters around whom the entire musical revolves, they have the highest degree. And King George has, unsurprisingly, has a degree of 0 because if you remember, in all of his songs are monologues. They're solo songs. He doesn't appear in any songs with anyone else. That's why it's a degree of 0, and also like see King George almost like separate from the rest of the graph. So again, like a very simplistic measure, it's just a count, and if you want to get like some quick numbers on the relative importance of vertices, this is a pretty useful measure to use. The next one I want to talk about, and it's again like very popular, it's called Eigenvector centrality. This is also known as prestige score. So as the name implies, it's a measure of the relative prestige of the vertex, or how much a vertex influences the rest of the network. And a popular implementation of Eigenvector is actually Google's PageRank algorithm. So one analogy I have is, say you own a website and you have a ton of SEO, and you have a lot of, you're trying to get a lot of pages ranked to your website, and you can still not make page 1 of Google, right? But a link from a really prestigious website, like say New York Times or Wall Street Journal or whatever, will carry a lot more weight for that page ranking, because a connection to a vertex with a high eigenvector score will contribute more than many connections to vertices with low eigenvector scores. So it's almost a recursive. Hope you've had an opportunity to do some guessing. The vertices with the highest prestige score are Hamilton, Bird, and Washington. Another corollary centrality measure is called Betweenness. So when I talk about shortest path problem, so there's that popular traveling salesman problem where the goal is to identify what is the quickest way to traverse from place A to place B, or from node A to node B, if you visualize a city as a network. So like how quickly can a traveling salesman get from like one place? So Betweenness is a measure of how many shortest paths pass through this particular vertex. So it's an indicator of how much the vertex is literally in between other vertices. Rather, how does it act as a bridge between different networks? If a node with high betweenness gets disconnected, it's very highly likely that it breaks that graph or the flow of communication. And an easy way to explain it is, think about our own real life relationships, for example. We have cohorts of sub-networks. You could have 2 different friend groups that you're part of, maybe your high school friends and your college friends, but you're sort of the missing link. You're the link who links those two discrete groups. or maybe you have maybe consider a network colleagues, your neighbors, and your family. Again, you would be the person with the highest betweenness score in a network like that. You're the link between all of those networks. So as far as betweenness centrality goes, so the three sisters, Angelica, Eliza, and Peggy, have the highest betweenness scores. And as I was doing this graph, I found it really interesting that the three men, Hamilton, Burr, and Washington, they had the highest prestige scores, and the three women are the ones who are the bridges. Like they sort of almost that the link, the bridge between the politics side of things and the family side of things. So again, like two different measures used widely in graph theory, but for two completely different things. So that was having some fun with Hamilton, but I also want to talk about a specific business application where I've used network graphs at Microsoft. So the problem statement was I was working with a wish list of new features requested by enterprise customers. And each of those requested features had been entered by product managers working directly with customers into a tool. And different product managers talking to different customers, we have entered in their own description of a desired features, but the ultimate goal would be the same. And this is all unstructured text data, so it's highly subjective and contextual, and very tricky to parse or even like identify if there are like duplicates between like two feature requests entered by two different PMs. So from a planning perspective for software development for the engineering team, it's super important to understand which features need to be prioritized. Like can we synchronize product development of related features, for instance, and to make sure that efforts are not duplicated. So just like with for the implementation, just like with the Hamilton graph, we defined a similarity index, a weight function. And in here, just like we saw Hamilton characters as the nodes, here the features are the nodes, and the edges connecting them are the similarity of the customers who were requesting both sets of features. So when we presented this graph, the stakeholders were immediately able to identify or like quickly discern which features are strongly correlated. It's intuitive, it's easily interpretable, and it prompted an immediate discussion of, oh yeah, it makes sense to synchronize product efforts for these two features because even though they've been entered slightly differently, they are in fact one. So this kind of approach is pretty valuable when you're not working with a too big data set, but when a black box ML model might not perform. And finally, to close out this part, some applications of network graphs. So if you think about it, the internet that we use every day, that's just like one huge network graph in itself, right? Social networking sites is another obvious example, things like Facebook or LinkedIn and Twitter, the whole friends you might know, the people you might know, they're all heavily making use of network graph theory concepts. Things like ride sharing, Google Maps, the traveling salesman problem to identify what is the best optimal path to place A to place B. Knowledge graphs, lexical and semantic processing within NLP. There's a fun 6 degrees of Kevin Bacon party game that you might have heard of, like to figure out how many people should you know in order to get to Kevin Bacon. And super prescient for our current times, epidemiology. So things like super spreader events, origins of pandemics, like how they're spreading, all of that again, like making of network theory. And similarly, even telecommunications is another option. And like I just demonstrated in this example, a fun application could be visualizing your character relationships in your favorite fictional universe. I just showed Hamilton as an example, and the picture that I have here is one where I did a similar analysis for Harry Potter universe. So lots of fun applications to. I hope this spark some creativity. The second part that I want to talk about is Engrams Analysis. So first we use the dataset to extract characters and relationships between them based on the songs that they've appeared, right? For the next part, we're going to focus on the actual lines of lyric itself. And I'm going to demo how you can extract engrams from those lyrics. So a quick refresher on engrams. So engrams are a concept used widely in text processing. So the technical definition is it's a contiguous sequence of n words from a given sample of text or speech. That's a lot of words to say phrase. So engrams are just phrases. It's Alexander, for example, is a 1 gram word. Alexander Hamilton is a 2 gram. So my name is Alexander is a 4 gram. My name is Alexander Hamilton is a 5 gram. So what are engrams used for though? So you can almost think of engrams as features that you get from text. So like you're almost like extracting the major themes from a given corpus. Corpus is just a document. So and engrams modeling is a machine learning application that makes use of these features. So one example that I've demonstrated here is autofill. Your phone autofill is a classic example where you enter in a phrase, your phone gives you like 3 possibilities in decreasing order of probabilities that this is the next word that you're going to type. Like if you type like have a good, you're probably going to get like have a good day or morning, or like I entered pancake as an example. But that is to demonstrate that it is in decreasing probability. And how does that know? Because it's a model that's been trained on like a lot of examples of, okay, this is how humans communicate, right? Like like have a good is usually followed by have a good day compared to the probability of saying like have a good pancake. An example from the Hamilton could be if you enter I'm not throwing away you're probably going to get shot, depending on the corpus that you trained on. So what we're going to do is we are going to extract engrams from the Hamilton data set and use something called a babbler to generate our own lyrics. Compared to the graphing example, this is fairly simple. It's really straightforward. All I need to do is collapse all my lines column into one big string and then just use the engram library, and voila, I get engrams. So what I've generated here is the top 6 grams. So these are phrases of 6 words each, sorted by the number of times that each phrase appears. So it looks like the phrase in the greatest city in the is the top engram, and based on the frequency with which it happens. So this is an example of a 6 gram. Just a few more examples. There's a 5 gram, 5 grams, a list of 2 grams, a list of 10 grams. So now this is a classic cold start problem where, okay, what is the right end to start with? And I think of it similar to a k-means problem where there's no one right answer. Like what is the right k to start with? What is the right number of nobody knows, you just have to play around with, sure, there are like some techniques to optimize finding that k, but for the most part, it's highly subjective, it's highly contextual and dependent on the problem at hand. So you just have to play around to find with n to find your optimal fit. So there's definitely a trade-off in considering a too high or a too low n. So if you choose and that's really high, for example, like 10, sure, you would get really good quality phrases, but you wouldn't get as much frequency. So, you wouldn't be left with a lot of training examples. And on the other end, you choose a 2 gram or a 5 gram, it might not always work in scenarios where like the example that I have is in the, like that's nonsensical. That's not something that I can realistically use. So either you'll have to spend some time like cleaning your data, maybe removing stop words and so on. So, but there's definitely like some kind of like trade-off that you might have to make in choosing that value in the right value of n. And like there's always that concept of like you can use a combination of words. Like you can use like 3 grams as a set of features, like 2 grams as a set of features. But typically bigrams and trigrams, so 2 and 3 grams, are fairly common. So now that like we have engrams, like how are they used, right? As far as applications go, engrams are used in a variety of unstructured text processing applications. So one example could be topic modeling. So it's things like just extracting themes from documents. Could be autofill, like I demoed. News classification. Does this news belong to politics or sports or entertainment? NLP, speech recognition, language translation. Again, like heavy applications of engrams and Markov chain models at play. As well as you could have fun Twitter bots. So then that I want to show an example where I've used the engrams that we generated in the previous 2 slides to generate my own random lyrics. Now these lyrics are nonsensical, like they're random, but they're obviously from Hamilton and in the similar style, right? So how does Babel work? So it extracts that set of engrams and then it scrambles it. It creates like a random scrambler and then it outputs something. So you can think of it as a potential application for a Hamilton Twitter bot, right? Or maybe you want to write something in the style of Shakespeare. So you train it on a corpus of you train your engrams on a corpus of all Shakespeare plays, or you want to send a fun text of your text of the day or something like that. So again, like not a lot of like, or at least I can't think of a lot of like businessy applications, but it's certainly. Right. So that was the last section that I had, but I do want to share that like all of the code that I've demoed. The credit to that data set is on Kaggle. These are the libraries that I've used. So dplyr for that transformation into an adjacency matrix, igraph for everything related to plotting and creating, and even all those like centrality measures. I spoke a little bit about Wish network or the dynamic graph where you can like drag and drop and click around. So again, like Engrams library is pretty potent. So that's my bio. So as I mentioned, Microsoft, that's my LinkedIn. Feel free to reach out to me if you want to connect or if you have any questions after the conference, or if you just want to chat about like life. With that, I'm going to close the session. I hope you found it useful. And